Okay, we're back. I hope that you took some time to play with the TensorFlow playground with the networks there and came up with some solutions to those tasks. Sometimes you have to wait a long time for them to converge, but just sit and watch them, and eventually they'll converge, and you'll see it. You'll see it happen. I'm not going to review that here, although we might just quickly go back and talk about some of those things, some of the things that were in that simulation. In the live class, that's when we'll play with it together, and you guys can share with me your solutions. So look to the live class for that. What I want to do now is want to talk about the next few sections of the handout. I actually kind of reached ahead on the last video, and I talked about backpropagation of error. So when these networks are learning, they are learning by doing a feed forward pass that gets the answer, and then a backpropagation of the error signal. So I basically covered everything that's in these two paragraphs here. The mathematics of backpropagation, like I said, are a little bit advanced, and the proof that it works is a little bit advanced too. So it's not part of the course, but it's a good idea to have a general understanding of what it is and what it does. So basically, if you've got a node in the middle of the network, you need to figure out how much error was this thing responsible for so that we can tune the incoming connections. Well, we just look at how much did we have to change each of the outgoing connections to this node. I'm going to make this a little bit bigger here. There we go. So if we're training this one here, how much did we change these in outgoing weights? How much did they have to change? And then we consider that to be some measure of how responsible this neuron was for the overall error of the network. And we use that as a scaling signal to change the incoming weights a little bit. So we can start at the output layer, like the perceptron learning algorithm. We look at the difference between the output and what we wanted. And that's our initial error signal that tunes these weights. And then when we want to know how to tune the weights coming into this thing here, we look at how much did its weight change, and we use that. And then for these middle ones, we look at how much their outgoing weights changed overall, and we use that as the signal going backwards. So that's backpropagation, also referred to as, it's backpropagation of error, is what it's called, sometimes called backpropagation or just backprop. So people will refer to multi-layer perceptrons or deep learning networks sometimes as backprop networks as well, to refer to them based on their learning algorithm. There's also a technical name for this process, which I think crops up in sklearn, which is why I put it here, stochastic gradient descent. Okay, and that's the descent idea that gives us this idea that we start in a sort of highly unstable place in the network, and we're sort of exploring this multidimensional landscape, trying to go down to a lower error signal, so a lower state of energy. And there are peaks and valleys in this landscape. If we're over here, then we've got a lot of error. If we're over here, we've got less error. But we can get stuck in a valley. We can get stuck in a bottom point where everywhere we move our weights to is going to be uphill, and we can get stuck there. So that's why sometimes when you run a network, it converges, and then when you run it a second time with a new set of initial starting weights, it starts in a different place on the landscape, and it does better or worse than it did the first time that you ran it. So gradient descent, where we're moving downwards through this energy landscape, through this error function landscape to a lower error. All right, that's very hand-wavy, but maybe you get the idea. We need to talk about activation functions. Okay, so the activation function is, so you work out the activation for a neuron, whether it's a perceptron or a neuron in an MLP. You work it out by multiplying the inputs times the weights and adding all that up. And you get a level of activation. So here's a little graph of the threshold function that we've been using. This is the output. So you will have a threshold. So here it looks like it's about maybe 1.2 or something is the threshold. So if the total activation is lower than that, we output 0. If it's higher than that, we output 1. So this threshold function works just fine for a perceptron learning algorithm, but it will not work for backpropagation because we need to have a function that has a derivative. And this doesn't really have a derivative. So because there's a break in the function here, we can't differentiate. Well, it's either a 0 or it's basically infinity. So what we tend to use is functions that approximate this step function, this threshold function, but are smooth. So this was one of the first ones that was used, the sigmoid activation function. So it goes also between 0 and 1. You can look it up. It's called the logistic sigmoid. I think here it is right here, logistic sigmoid. Okay. It's a complicated function, but basically it has a limit. It has a limit of 1. So as we go out higher and higher activation out here, it just gets closer and closer to 1, but never reaches it. And as we get lower and lower activation, it gets closer and closer to 0, but never reaches it. And then there comes a point right here where it almost kind of steps up. And you can tune this function a little bit to make the step more and more like the step function of the threshold over here. So you can think of this function as having a threshold at about 0, more or less. But it has to be quite a bit below 0 to be basically a 0 output, and quite a bit above 0 to be a 1 output. So this was one of the first functions that was used. Nowadays, people tend to use the hyperbolic tangent function, which has a similar shape, but it goes between -1 and +1 instead of between 0 and 1. And I think the introduction of negatives here helps. This is often a network will drive to convergence a lot faster using hyperbolic tangent function. And you can see these functions, by the way, if you go into the TensorFlow playground over here. I don't know if you played with these, but the default, I think, is tanh. So the hyperbolic tangent function. This is the sigmoid function here. And then there's a couple of others, which we'll take a look at as well. So when the big breakthrough happened, and we coined the term deep learning to account for it, the big breakthrough with convolution networks happened with a different kind of function called the rectified linear, which is this. The function, so x is the activation. The output of that function is either x or 0, whichever is greater. So what that looks like is this. There's kind of a dividing line at 0. If the activation is less than 0, it's just going to output 0. If the activation is greater than 0, it's just going to pass through the activation. So it's really fast to compute. It's just a single if statement. There's not a lot of math involved, which tends to slow things down. This is how it compares to this. This is the green is the sigmoid function, and the blue is the hyperbolic tangent function. And yeah, it goes up to infinity. It doesn't bother to stop at 1, but it seems to work quite well. So you can find this in the playground over here. It's ReLU. So these are referred to as ReLU units. And you notice it's going between 0 and infinity, basically. So we no longer have orange colors here. So when you run this, you get, oh, look at that. That worked pretty fast. You get, oh no, it's still, oh yeah, the weights still go negative, and the output function is not a ReLU unit. The output function is something different, I think. I'll have to look into that, because the output function is clearly still outputting negatives, even though the input functions here are not outputting negatives. That's a little preview of a network architecture that will solve that one task anyway. Where was I? Yes, so the rectified linear function, or the ReLU units, rectified linear units, will work quite well. And there's also the linear function, which is just f at x equals x, so where x is the activation. So that would just be a straight line at a 45-degree angle going all the way down here. The rectified one bottoms out at 0. The regular linear just goes all the way down. So that's a really cheap activation function as well, and it's here too. Whoops. Yeah, linear, run. Yeah, it might be a little bit harder to get this one to do what you want it to do. Yeah, there's something different about the output unit. I think the output unit is fixed as just a linear unit. That explains why when you use sigmoid, for example, this one's not going to work all that well, but you can see there are negatives here because there's a high negative weight here. Even though the units are only outputting between 0 and 1, they can send a negative signal in. Oh, look at that. I love watching these things go. And this, I think, is just a linear unit. I think the output unit is just linear. That's what's going on there. Meaning whatever the activation is here is just passed through as the output. Okay. So anyways, so we have to have a different activation function. We can't use the threshold function, at least not for the internal hidden units. So sigmoid is the oldest one that people used. Hyperbolic tangent is another one, and rectified linear and linear are modern ones that people use. The sigmoid has some support from biology, less so hyperbolic tangent, but the rectified linear, even though it looks kind of weird, also does have some support when you look at how real neurons work. If you interpret the output as a frequency, it has a little bit of biological motivation as well. Okay, what else do we need to talk about? Oh yeah, non-binary classification. So what do you do if you have 3 classes, right? So far we've looked at every unit we've looked at, every network we've looked at only had one output, so it could only do one class. Well, if you have multiple classes, like say you have 3 classes, what you can do is you can have a network that shares the same hidden layer, but at the or hidden layers, but at the output layer has multiple outputs. So if we were to change this network up here to a 3-class problem, we could add 3 units here and have these ones fully interconnect. And basically what you're trying to train then is the first unit. Let's go back to the picture here. This unit will do class 1, this unit will do class 2, this unit will do class 3. So and it's kind of like naive Bayes. Whichever one has the highest output would be the one that you would use to classify if you're looking for an exclusive classification. If you're okay with putting 2 classification labels on the same example, then if this one and this one are both close to 1, you can classify it as both class 1 and class 2 and use this as class 0. Okay, so you see that quite a lot. The output layer has multiple nodes, and basically you're computing 3 or 4 or 5 different classification problems, all sharing the same input. So then here's an example here. The target outputs are binary vectors. So, okay, the iris data set. There are 3 classes called 0, 1, and 2. So this might be your 0 classifier, your 1 classifier, and your 2 classifier. If the output is supposed to be class 0, then what you're looking for is 1, 0, 0. So the output signal may come in 0, 0, 0. The correct was 1, 0, 0, so you apply the learning rule to all the weights based on that. So you want the first one to output 1 and the others to output 0, or as close to 0 as you can. Okay, so you can repurpose a single network to do multiple classifications in this way. Here's a little exercise for you to do. Let me just snip this out. I'm going to use my full screen snip here. So this is I can't ask you to simulate the backpropagation step. It's too complicated. But let's snip this out so that I can draw on it. So what this is this is a picture of a neural network with 2 inputs. I put the inputs as square. You'll often see that the neurons are round and the inputs are square. And then these numbers here represent the weights, and they're all integer. They're mostly integer weights, just to keep it simple. So the idea is I want you to do the feed forward step here. So I want you to compute the activation, which you could put here, and then compute the output, and then compute the activation of this node and the output, and so on. So how we would get started on this is we could take a look here at this unit here. So we want to know the output, the activation and the output of this unit. So the input is, so for that unit is -2 times 0.5 plus 0.1 times 2. Actually, yeah, that's right. 2 times 0.1, which is equal to -1 plus 0.2, which is equal to 0.8. So that's the activation for that neuron. If we want to know the output, we are going to have to find out the activation function. It says here the output function is tan h for all of these nodes. Okay, so we can go back to this. We figured out that the input, I'm not going to ask you to if you want to, you can figure out what the tan h function is and figure out the exact number. use a calculator or whatever. But here we've got, I'm just asking you to eyeball it. This is the tan h function right here. We're at about 0.8, which is about here maybe. So if we take a look here, looks like about, what would you call that, 0.7 maybe? Let's go with 0.7. So the output here is going to be 0.7. So that's the exercise. Figure out the activation and the output for each layer, and then feed that forward and figure out the activation and the output here, and then finally the activation and the output here, and figure out the final output. Oopsie. There we go. So that's the question. So just a quick little exercise, and I think I noticed just now, I think you can see that I took this from an old test because I accidentally left in how many points it's worth. So this is for 5 marks, whatever that means. Okay, so quick little exercise to do that, and then we will take a look at some code in the next video, and we'll take a look at the assignment. Okay, so I will see you in the third and final video.